have, this is how it's defined. Transfer function of a kernel power system is EV over S plus A. Therefore, response CS is step response is EV over S into. The time response so if I do a plot T, C of T, the response and this is the initial slope. And so we defined a few terms. The first quantity is called time constant. Before we define this in time constant, so initial slope is simply equal to 1 over time. Okay. So you can say now let's define time constant. This is very important. If all of these terms are defined in this context. Okay. Then you have rise time. this time represented by PR is equal to defined as time for the waveform to point 1 response to So this is a unit step response, correct? What is the final value of this? What is, let's say, if I ask you, what is C final of T?
Is that a TR at the bottom? TR.
Raise time.
Oh, that's
1 minus e to the minus 18.
So that is T. That is C of T. But what is final? How do you compute final? How did I say we compute final? What is initial? You have to look at this. Can you compute the initial and final from this?
Isn't that what you had said briefly about starting at 0 and then for
Why
0?
is it 0?
Well, from what I recall, 0 was the point on the graph. You know what I'm talking about from last class?
Huh?
It was 0 because that the e to the minus 0 makes 1 and 1 minus 1.
What makes it 0?
The 1 constant.
This time is going from what? Time will always go from there is
From 0 to infinity.
0 to infinity. Whenever you do something, time will always go from 0 to infinity. So C initial would be
0.
Ct computed at t equal to 0. This would be Ct computed at t equal to infinity. So this would be 1 because e to the power of minus infinity is
Such a small value.
0. It's 1 over infinity, which would be 0. Okay? So it will be 1. This would be 0 because e to the power of 0 is 1. 1 minus 1 is 0. Okay, this is time. It's simple.
Time always goes from when you're starting a system. That's when you start that system. That is 0 time. So you compute it as time goes to. So the final response of this, since this is keep in mind this is unit step response. Okay, that is what is very important. Unit is very important. So this could be, if this was not a unit step response, if it had 2 units, 3 units, this would be just 2, 3, that. Okay. So since this is a unit step response, you are seeing that the final value will go to 1. Ultimately, the response will go to 1. Okay. It will just be like the input. Time constant is simply defined as this 1 over a. Okay, this is the initial slope. This will define. See, this is the only quantity which will define how your waveform will look. This 1 over a. All right. This is the only variable. Time itself it's a fixed. Although it's a variable, it's a fixed variable. It will not have any other. It only goes in certain direction. It has a certain interval. Okay. So this is the only one. This is the only quantity variable which defines how the system will flow. If this is, so you see how this curve will slope based on this a value. That is the time constant. Now, what is the rise time? Rise time is simply the time taken by the system to go from 10% of the final response to 90% of the final response. So if you're looking at, let's say, if you're looking at vehicles, so you say 0 to 16, so many seconds, so many minutes, right? So that is what this is. This rise time defines that.
And that 2.33 and that 0.11, where'd that come from?
So 2.33 is 90%, right? So you substitute C of t equal to 90%, 0.9.
Mm-hmm.
Okay? 0.9 is fine, 0.9. Then you compute this t.
Oh, and that's going to give you.
That's what it's going to give you. Okay?
Mm-hmm. He's saying, I'm going to do my calculator to make sure I'm with you.
So this is what? Time taken, right? Substitute C of t equal to 0.9, 90%. And calculate this t. This is the time taken for that 90%.
A is, oh yeah.
What's A?
Oh, A is still there. See, at the bottom.
So what would this be? It will be 0.9, right? Take this on the other side. It will be 1 minus 0.9. Okay? That will be 0.1. Then you calculate this t. It will be natural log of 0.1. What is natural log of 0.1?
I think we got the wrong value in our calculators. I think we got the wrong idea. So when you 0.9 is the time. 0.9 is your t.
C of t. So 0, this is 0% of the final response. This is 100% of the final response. So 90% would be somewhere here. So you have to go for that 90%, wherever that is, and calculate the time taken here.
Okay, I was plugging in the wrong thing.
So substitute 0.9 here, C of t, and calculate this t. Do you get it?
Let's see. So it's 0.1 on the other side, and then he said
Yeah, you gotta get rid of YouTube. Well, that's another
okay.
Like that?
Well, I got 2.30, but yeah. And the negative is because of the negative. Yeah.
So if you do the same thing for 10%, you'll get this 0.11 over 8. If you take the, so this is the time taken. This is the time taken for 90%. This is the time taken for 10%. So if you take the difference, that is what will give you the time taken for between 10% to 90%. That is the rise time. Okay. The next one is something called settling time. Settling time T of S, let's define this. Time taken for the waveform to reach and stay within 2%. 2% of the final value. This will simply be TES is 4 over. Okay. So we'll take an example and see what this means. You'll be given something like this. For a first order system, and G of S is equal to 50 over 1 plus 50. Find time constant. ER and Px. So what would be the time constant? Solution would be, and let's say I'll introduce here, find the unit step response as well. Okay. So the first one, so you have 4 quantities. You have to find unit step response, time constant, rise time, and settling time. Simply, what is the response of the system?
50 over S times S plus 50.
Right. So you look at first one, response. You say C of S would be R of S into G of S, where R of S is 1 over S. So you have this 50 over S into S plus. Now what you need to do here is, this is not complete here. You have to do C of t. C of t would be sum k1 plus k2 e to the power of minus 50 You have to find this K1 and K. Okay. Then you have time constant. What is time constant? Right. Time constant is simply equal to 1 over 50. This is 0.02. Then you have PR is equal to 5.2 over 50. Any this is how will be required to required to find these characteristics of a first order system.
Can I relate this to a real world?
Hmm?
Can I relate it to a real world system?
So that's what I told you, right? What is this rise time? Rise time is how fast you can accelerate. This rise time has to be, if you're looking at a fighter aircraft, the rise time has to be really small. Okay?
Time it takes to
It has to speed up really fast. It has to get to that final, whatever final this thing it is trying to reach, very fast. John Lewis, is that important? The settling time is the time it takes to settle. Right?
Was it
Huh?
close to the straight and level?
Yeah, once it stabilizes. So it is just whatever final value it is trying to reach. 2% of that final value to stay within that 2%. Right? So it may never reach the final value. Any of these systems, they are never going to reach 1. It will always be around that 1. So what is acceptable is, let's say you define this 2%. Within 2% of the final value. So if you're looking for a particular altitude, it may never reach that altitude, right? And you cannot really maintain that altitude all the time. You'll be like kind of doing this. You cannot precisely maintain that altitude. Yes.
So C, although the C of T, C final of T, although that'll never reach 1, can't C initial be 0?
Yeah.
Okay.
It has to be 0.
Okay. But that CT of final is not really 1.
The C of T is final, but it will not reach that. Practical systems will not reach that.
Okay. Well, with practical, okay, yeah, because practical systems can reach the initial, because that's the starting point.
Right.
Okay.
So if you're trying to reach a particular speed, particular altitude, an aircraft, it will never reach that, right? It never. Have you really tried to maintain, even in a cruise control, can you really maintain the speed you're trying to maintain all the time? When it's going up the hill, it will slow down, right? So that's what it is. This thing will be slightly off. Huh?
It's kind of like point of error.
Right. So what is an acceptable error here? It is 2%. So that is what you define for your system.
How
It
do
could
you
be.
decide that point of error?
That is up to you. That is up to the design engineer what is acceptable. So what is acceptable in an aircraft? So if those are defined by the aviation policies, the aviation regulations tell you have to be at least 100 feet, you have to maintain at least 100 feet or 20 feet or 30 feet between two airplanes. That defines the error.
And that numbers we get through like some kind of experiment that has been gotten.
That's just experience. You do some experiments, you figure out what's a safe distance to here, and then you decide.
So like even if you discuss
What is the distance of the distance you have to maintain between two cars?
30 feet.
Huh?
30 feet. Oh,
2 second difference, right? If you're going, so how do you determine that 2 second?
I usually count.
How do you determine? How do you come to that 2 second difference?
Human response.
Human response time. So if you, whatever speed you're going at, if you look at an average vehicle, if you try to brake it, it may take 2 seconds to
Respond.
stop the collision. That's how we do it. That 2 seconds is an acceptable answer. So if you're looking at, it depends again on, if you're looking at a robust system, if you want a robust system, you compromise on performance.
This.
Okay? If you want a highly performing system, you compromise on robustness. Okay? Robustness. Yeah. If you're looking at
Like trucks and stuff.
passenger aircraft, you're not so worried about the performance. Right? You're not looking at high performance. You want it to be fail-safe. You want it to be robust in design. So you compromise on performance. But if you're looking at a fighter craft you cannot compromise on performance. Right? You have to have that performance.
but in that condition, then you have to consider both.
You consider both, but you actually you let go the performance a little bit. You have to let go. You cannot. You don't design a fighter craft with turbofan engine. Do you? Have you tried to design a fighter craft with a turbofan engine?
No, that's
It will not give you that performance. Have you? You would go with a turbojet.
What type of time is TS?
Huh?
What type of time is TS?
TS is settling time. For example, if you're going on the road, if you're going on the highway, if you're what is the final speed you're going to do? Going to go 70, right? So if you go to if you want to go to 70 miles an hour, the time it takes to get to that 70 or between 2% of that 70 and stay there.
She never goes 70.
Huh?
She never goes 70. Michael be speeding on that highway.
I just go 80.
You go 70, she goes 70 in the city. Alright, let's introduce. I'll just give you. Alright, we'll just introduce second order systems, okay? So in comparison, if you're looking at the first order system, huh? This one is not, this chapter is not.
We hope it will.
Huh.
It looks easy.
But we don't.
Right, it is easy actually.
It's included.
So typical second order system is defined by like this. B divided by okay. So you can see that the polynomial here is polynomial in the denominator is a second order polynomial. That is the reason this is a second order system. So when we are talking about second order systems, we have 4 categories
second order systems. Okay. The first category is roots of denominator real and distinct. Okay, so this is essentially these are the possibilities. Mathematically, these are the possibilities. There is no other possibility that exists. There are only 4 possibilities that exist. Okay, so the first possibility is roots of denominator are real and distinct. Example would be nine over square plus minus plus 9. Okay. So you can find the roots of the system very easily. Just use a calculator or The second possibility is
It is. It's supposed to.
roots are complex. So an example would be third possibility is roots are real and repeated. So let's do this in this model. Roots are imaginary. Let's do this first. We have an example would be 9 over square. The final possibility is roots are real and repeat. Nine over square. So this is called an over-damped system. This is an under-damped system. This is an undamped system. This is critically damped. And if you look at the waveform of this, I'll just explain this and we can wrap it up here. Okay, this is an undamped system. This is overdamped. This is overdamped. This is underdamped. Undamped. This is critical. So if you look at this, should make sense to you. Overdamp. What is damping? What does damping do?
Bring it to its original position.
Huh?
Bring it to its original position.
Right. So if you look at think about the doors, right? All these doors, most of these doors have those hydraulic dampers, hydraulic stops. So if you're looking at such a system, an overdamped system, so if you try to close it, it will go really slowly. Okay? For this. For an underdamped system, what will it do before it closes? From the waveform, can you make out what might it do?
At first it will be like fast and then it will go slow.
So this is the final position. Okay, these dotted line is not the final position. What is the final position of the door, of such a door?
For what?
Close.
Close it, right? So it will, if you are looking at an overdamped door, it will go very slowly and close. Okay. For an underdamped, it will do that. It will go beyond the closing point, come back, go, come back.
Like those doors, like in the where the cooks are, like it goes both ways.
Right. So that is what it will do. Okay. For an undamped system, it will never close. Undamped system is marginally stable system. It will keep on oscillating. Critically damped is the best system you can have. Okay. Critically damped system would be, it will close perfectly. It will only do one this thing and it will close. Okay. This system, what is the limitation of this system? Here, if you look at in terms of these same quantities, of course this is a second order system, but it will take a lot of time to get to the final result. Alright, but it will be robust. It will not overshoot. This will take less time, but it will overshoot to reach the final result. This will never get to the final value. This is between this and this is this, which is what you want, what you're trying to do. And this is the ideal system. So we'll continue with this discussion next class.